Alright, so this is a video that's supposed to explain how the trig functions are defined for any angle. Just to look at what this is here, we have I have the coordinates of the point here, P, coordinates of P. R is the radius of the circle or the hypotenuse. The angle theta is the central angle here. A limitation of that is I can't show angles greater than 180 degrees. I can do small angles, and then we can go, if you watch here, right? It's going up to 90, and then it'll go all the way to 180. But if I try to go past 180, the angle falls back down again. But you get the idea. You know that these are angles greater than 180, and we can go all the way to 360 and around and around and around. So what we're going to be looking at is the trig functions here. First of all, notice that when I change the size of the circle, which changes the size of the triangle, the trig functions do not change. That's because all the triangles are similar, and the functions are based on the ratios of the sides. But no matter how big they are, the proportions are all the same. So it doesn't really matter how big a triangle I use. For now, let's just concentrate on sine. All right, the sine of the angle is the ratio. It's the ratio of this side to this side. So it's a fraction. All right, with this side being the numerator and the hypotenuse or the radius being the denominator. So when we have, check out what happens to the sine function. You got to watch here. As the angle gets really small, the opposite side, the vertical piece, is getting small relative to the hypotenuse. So that would account for the fact that the sine of 0 degrees is 0, because the opposite side, the vertical side, is 0. And as the angle grows, what's happening? The opposite side is growing, but the hypotenuse is staying the same length. So what's happening to their ratio as the opposite side grows? It's going to get bigger, right? How big is it going to get? Well, if you look up here at 90 degrees, the ratio of this side to this side is going to be 1, because they are approaching the same length, right? So the sine of 90 degrees is 1. So when you think sine, you should your concentration should be on this, right? When you think sine, you should think up and down. Sine is vertical. Associate sine with this side here. So it's basically what's going on with the ratio of this to this. So let's just kind of study this a little bit further. It starts at 0, and then as the angle goes to 90 degrees, both of those sides meet, and you get the sine of 90 is 1. Beyond 90 degrees, what happens to that opposite side? It starts to fall again. Well, it falls. So then the ratio is going to shrink, right? Watch, see, 1, and then 0.9, 8, 7, 6, 5, and all the way down to 0 again. So the sine function goes through like half a cycle here. It goes 0, 1, 0, and then beyond 180 degrees, you look at it and the sine is negative. That's because it's really based on the coordinates of this point P here. All right, check it out. The y coordinate, if you consider the vertical side of this, it's really the y coordinate of the point P, right? So since the y coordinate is negative, the sine is going to be negative. The way that I look at it, though, is that I just think if the vertical side is up, then the sine is going to be positive. And if the vertical side is down below the x-axis, it's going to get counted as a negative quantity. Right? So up means positive and down means negative. For definitional purposes, the hypotenuse or the radius is always counted as a positive quantity. So in the first quadrant, opposite and hypotenuse are both positive, so the sine is going to be positive. Second quadrant, opposite and hypotenuse are both positive still, so the sine is going to be positive. But when we switch down here, because this length is downward going, it goes down, this gets counted as a negative quantity for purposes of calculating the sine. But this still stays positive just by definition. All right, so it makes a nice smooth transition from being positive to 0 to negative. So then when you go all the way to 270 degrees, the sine of 270 is going to be -1 because both the opposite side and the hypotenuse are the same size, but because it's down, the opposite side gets counted as a negative quantity, and so it's -1. Beyond 270, what you see is that the size of the opposite side is shrinking, but it's still negative. So it's going to be negative, but approaching 0 again, whereupon it hits back here again, and then it just repeats itself. So sine, when you think sine, basically just think of this side here and what's happening to it. This might be a little more clear if we use the unit circle. What I hear about a lot is the unit circle. Why do we use the unit circle? That's a circle whose radius is 1. So if I try to change this here, I can change the radius of the circle here if I try to get it just right. So that's pretty close. You can see that the y coordinate and the sine of the angle pretty nearly match, right? If the radius is exactly 1, and the ratio and sine is the ratio of this side to this side, then really the sine of the angle is going to be this length divided by 1. That's why these two numbers match when we use when the hypotenuse is of length 1. So this is like another way of thinking about it. If you if you use a unit circle or a hypotenuse of length 1, this length, the y coordinate of this, is the sine of the angle. These things are always going to match. So if I just de-emphasize these for a second here, if I dash that and I dash this, and so you can think of sine as the length of this bolded side here, positive and negative as a case may be. So it's 0, and then it grows to 1, and then it shrinks down again to 0, and then because it's down, it's -1, and then goes back to 0, and on and on and on again. If I just kind of go around here, if you just kind of soft focus on this and just look at how the length of that opposite side is changing, right? Up, down, up, down, up, down. That's what accounts for the waveform that it makes. Alright, so that's enough about sine. Let me do these again. So we want thick and thick. Let's talk about cosine. Cosine is very similar. Cosine is adjacent to the hypotenuse. So cosine, it's all about this side here. Cosine is the ratio of this side to this side. Alright, so without looking at it, try to figure out, if I bring it down here for a second, get that out of the way, what's happening to the ratio of this side to this side as, say, the angle gets small. The ratio, alright, remember, this is the numerator and this is the denominator. So as the angle is small, we would say that the cosine of a small angle should be relatively large, because for small angles, the adjacent side, the adjacent side and the hypotenuse are about the same size. And at 0 degrees, they are the same size. So the cosine of 0 is 1. So then, and that's right, cosine of 0 is 1. So then you would conjecture what happens at 90 degrees. All right, 90 degrees, the adjacent side is shrinking. All right, it's going down. So then the ratio should be falling. Since the adjacent side measures 0 here, the cosine of 90 degrees is 0, and it is. Look at, so let me bring this back here. All right, the cosine of 90 degrees is very small, is 0. And then what happens when we go past 90 degrees? Since cosine is based on the horizontal piece, this gets counted as a negative quantity because it's left. All right, to the left, this gets counted as negative in the same way that this gets counted as negative when it's down. So it's more about the x coordinate of this. But if you just think that left is negative and right is positive, you pretty much can't go wrong here. So after it reaches 0, it goes in the negative direction. Right? It's all about this piece here. And so the ratio at 180 degrees should be just about -1. Right? Because they're the same size but opposite in sign. And then what happens as we go past 180 degrees? Once again, the horizontal side shrinks This shrinks into 0, right? It's going down, 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 whoop, vanishes. So the cosine of 270 is 0, and then it grows back again to 1. So if we want to do that soft focus thing again, you can see what happens to cosine. Whoop. All right, cosine. If we use a unit circle, which we have been using, the radius is 1. So cosine is the ratio of this side. It's this divided by 1. So this length is the cosine of the angle if it's a unit circle. So then again, you just soft focus on it, see what happens to it, right? It starts out at 1, and then it shrinks to 0, and then goes back out to -1, and then shrinks again to 0, and then back up to 1 again. And that's what accounts for the fact that the cosine wave does this up and down stuff too. When you think of cosine, think horizontal. You should associate cosine with a horizontal length and sine with a vertical length. But this also accounts for the fact that the sine and cosine graphs look very similar because, well, just look at how they're defined. They have very similar characteristics. So that's cosine. Let me just do this again. So we want thick, and then thick again. And tangent now. Tangent is the ratio of opposite to adjacent. So tangent is, this is the numerator and this is the denominator. So it's a little bit tricky because they're both changing as the angle changes. But just think, this is numerator, this is denominator, and the sides and with the positive and negative conditions still being imposed. So everything is positive here. The tangent, which of the, just try to make a guess. If we kind of hide this, get it off the thing there for a second, make a conjecture. Which should the tangent be of a small angle? Tangent of 0. Think about fractions with this tiny side as the numerator and this relatively large side as the denominator. The tangent of 0 should be a small number. And it is. The tan of 0 is 0. Right? Because the opposite side is 0. And then what happens as the angle grows? Well, there's like a double effect happening here because the numerator is growing and the denominator is shrinking. So that's going to make for something that's growing larger and larger and larger, right? Watch this. So the numerator is approaching whatever the radius of the circle is, and the denominator is approaching 0. So watch how it blows up. We're at 11, 15, 17, 18, 23. We can make it as big as we want. All right, and if I get real close to 25, I can make it as large as I want because the closer I get to 90 degrees, the smaller the denominator is becoming. And when we divide numbers by small numbers, we get really large numbers as a result. So the tan of 0 is 0, and then it's going to grow and get infinitely large. It can be made as large as possible. And then beyond 90 degrees, the same thing is happening. The only difference is it's a matter of sign, right? Look, tangent is negative, but it's real big. And tan is positive, but it's real big. So, but then, right, so we're getting this positive side divided by this negative side, right? Because it's left, it's negative, and because it's up, it's positive. So, and that's going to shrink down again to 0. And then when you come here, right, now both of these get counted, both the opposite and the adjacent get counted as negative quantities, so their ratio is going to be positive. So watch what happens again. All right, it's going to start off at 0, and then once again, since the denominator shrinks to nothing, it's going to blow up again in the negative direction. All right, negative numbers. See how big, right? We get like numbers in the thousands there, and then it's going to come back up and go back to 0 again, whereupon it repeats. So these are the basic definitions of sine, cosine, and tangent. It doesn't really matter how big we make our triangle. Everything is similar. Doesn't matter what our scale is. Right, everything stays the same because of similarity. And so when we go to figure out, say, the cosine of, let's suppose that we, just a quick example, if we needed to do, say, the cosine of 120 degrees, what's going to happen is we're going to locate 120 degrees, which is about here, right? And then what you do is, since, suppose we want cosine. Alright, so the cosine of 120 is this angle, and it's going to be adjacent to hypotenuse. So we know that the ratios of the sides are 2, 1, square root of 3. So because it makes a special right triangle, we would take the ratios of the sides of these, and it's going to be the same no matter what. I'll show examples of that. I can't really show it on here, but this is the basic idea about how the trig functions are defined. Just before I end this, I always like to do a real quick exercise just to make sure you know at least where the trig functions are positive and where they're negative. So you should think of sine as being up and down. So sine is positive in the first two quadrants, right? Check it out. And then it's negative whenever the triangle is down, for angles that terminate down here. Similarly, cosine is positive in these two because cosine is left-right. So cosine is positive over here and it's negative over here. And tangent, since it has to do with sine and cosine, tangent is actually the ratio of sine over cosine. Tangent is going to be positive wherever sine and cosine have the same sign. So tangent's positive in the first quadrant because sine and cosine are positive. Because sine and cosine have opposite signs here, tan is negative. Because both sine and cosine are negative down here, tan is positive again. And then because sine is negative and cosine is positive in the fourth quadrant, tan is going to be negative. So what I do is I point to a quadrant and I say sine, cosine, or tangent, and you should be able to tell me pretty quickly if you understand this up, down, left, right business, whether the trig functions of the angles that terminate in that quadrant are going to be positive or negative. Well, I'll just kind of hide this off on the side here, and I will point to a quadrant, and so this is how it goes. I'll go around and I'll say sine. And the answer is, so you would say positive because the angle is the angle terminates with its vertical piece up. So sine is positive in these two, and sine is positive in the first two quadrants. So if I say second quadrant sine, you say positive. If I say second quadrant cosine, you say negative because it's left. So it's all about this left, right, up, down stuff. So what I'm going to do is try this out a few times. You might want to keep your cursor on the pause button so you can pause after I say it and then make a guess and see how you do. So I'll stop on a quadrant and say a function and see if you can get the whether it's positive or negative. Okay, so ready? Cosine. The answer is negative because it's left. Sine. The answer is positive because it's up. Cosine. The answer is positive because it's right. Sine. The answer is positive because it's up. Cosine. The answer is positive because it's right. Sine. The answer is negative because it's down. Tangent. The answer is negative because sine is positive and cosine is negative because it's both up and left. So cosine, the answer is positive because it's right. Tangent, the answer is positive because it's both left and down. So sine and cosine are both negative. And cosine, the answer is negative because it's left.